All right, we're going to keep this nice and short and sweet, pretty easy. This is Congruent Chords, and this is 10.2 in your books. I didn't throw any music in there, but I did throw a nice little explosion for the transition. So anyway, our objective, we have 1, apply the relationship between congruent chords of a circle. Okay, nice and easy. Theorem 77 states that if 2 chords of a circle are equidistant from the center, then they are congruent. So you can see by the tick marks on this, let's say this is the center, that these lines here are congruent. And you know that this is a right angle. So this is perpendicular, and it passes through the center, which means that this is a perpendicular bisector, something to keep in mind from 10.1. It's an important one to remember. So just remember, if a line passes through a chord and the center of the circle, then that is a perpendicular bisector. So that's Theorem 77. Theorem 78 states that if 2 chords of a circle are congruent, so if we know that this chord here and this chord here are congruent, then we can say this, that they're the same distance apart. So if you drew a line, which you might have to do is using auxiliary lines, is draw a line from the center to the chords, that those lines will be congruent if the chords are congruent. Boom. All right, so some practice problems. We're given circle P, and we're told that PQ is congruent to PR, and that AB is 6x plus 14, and CD is 4 minus 4x. Now, since these 2 segments are congruent, that means the chords are equidistant from the center. So because of that, we can say the chords are congruent. So we can set AB and CD equal to each other. 6x plus 14 equals 4 minus 4x. Combine like terms, so get your x's on one side, your constants on the other. And that's going to give you 10x equals negative 10, which means that x will equal negative 1. Now, don't get thrown off by the negative, okay? X is negative 1. The measurement is not. So this isn't a measurement. We're just plugging that back in. So we'll plug it into AB since that's what we're trying to find. We'll plug it in for x. So 6 times negative 1 is negative 6 plus 14 equals 8. So AB equals 8. Easy enough. Let's move on to a proof. So we're given circle O, and that segment PQ is congruent to segment TS. Okay, so that means that these 2, which are chords, are congruent to each other. And we need to prove the triangle ROY. Oh, wait, where's ROY? Is congruent to triangle ROX. Well, where are those? We'll figure it out in just a second. So we start with our given. Simple enough. And then we can draw in those lines, that X and that Y. So we can say segment OX, segment OY, and segment OR by auxiliary lines. And then we can say that OX is congruent to OY because if 2 chords are congruent, then they are equidistant from the center of the circle. We can then say that OR is congruent to OR by reflexive, a lot of yours favorite reason. And then we would say that angle OXR and angle OYR are right angles because the perpendicular bisector of a chord passes through the center of a circle. So if this passes through the center, which these 2 do, then it's a perpendicular bisector. And now look, we have 2 right triangles. What do we do with that? Well, first say that angle OXR is congruent to angle OYR because they're perpendicular, so right angles are congruent. And then we can say that triangle ROY is congruent to triangle ROX because of hypotenuse leg. So just an example of how that would be useful in a theorem or in a proof. And you will be using it in, I believe, on the test, that this one, actually a bunch of these get used in the proof. It's not this exact proof, but just wanted to introduce you to it. But like I said, this is a short unit, and that is it. So, you guys have a good one. Peace out. Have a good evening. Enjoy the short video.